So for fructose, I'm going to make sure that we're talking about D-fructose here. There is the ketose form of it. And just like when we talked about with the glucose, the ketose form of this is left, right, right. That's the arrangement we have of the hydroxyl groups in this. And let's just draw out the chain here for a second. So we know that it's a ketose, so it's a ketone, OH like that. That's the first carbon, that's the second carbon. Third carbon, fourth carbon, fifth carbon, and then the sixth carbon. And just like with glucose, the sixth carbon is achiral. And then the next is just the following progression of the hydroxyl groups, the left, the right, and the right. So I have a hydroxyl group on the left, I have one on the right, and then another one on the right. It's the only really variable region between those two. And then fill the rest in with hydrogens. Handwriting is getting pretty sloppy. I'm a little tired. Let's number our carbons. Carbon number 1, 2, 3, 4, 5, and then this guy is number 6. Number 6. So that's it for that. Now let's talk about, for fructose we have the cyclic forms. Right, and there for the cyclic forms we have these 6-membered rings, and then we have the 5-membered rings. So for the 6-membered rings, these are otherwise, remember, they're known as pyranoses. The full name of the 6-membered fructose would be fructopyranose, which is kind of certainly is a hell of a mouthful. For the 5, remember we said that resembles the furan, tetrahydrofuran, right, as a solvent that we use in organic chemistry. So we would call this D-furanofructose. Anyway, so the 6-membered rings, just like when we talked about glucose, there is an alpha version, and then there is a beta version, and I'm not really going to compare and contrast those like I did with the glucose video, but know the differences between alpha and beta sugars, and then if you're ever lost, think about the chair conformations in the equatorial versus axial plane. So just like before, for my alpha configuration, I'm going to start off drawing my 6-membered ring in the Hayworth projection, or Hallworth projection, however it's pronounced. I'm so shitty with names. Keeping in mind that these things are kind of coming out of me at the plane, but I feel like that just makes it look too messy. And then I'm going to kind of draw out my things that are going up and then things that are going down parts. Alright, so this is an alpha sugar. Right, so if it's an alpha sugar, I know that my OH goes on the bottom, and then this would be an H if this was an aldehyde, but since it's a ketone, the R group goes on the top. So thinking in minds of axial versus equatorial planes, the differences between these two, the structural differences, and then the functions that those are going to give. And then the rest of it is just really the patterns that you follow that's very consistent with this. So we have a down, up, and then these two are going to be obviously matching with each other. So there's an OH there, an OH there, and then an OH there, because these two are together, and this guy is opposite. Then for the rest of it, we just fill it in with hydrogens. This is the easiest one of all the 6-membered rings to draw. So now let's number our carbons and talk about what we're dealing with. So this right here, this is number 1 from this. This is the R group. It doesn't really change too much. This is number 2 right there. This guy is number 3. This guy is number 4. Number 5. And then this is carbon number 6. So what you may or may not have noticed is that when we're forming a 6-membered ring, I love this, a 6-membered ring, the 6' hydroxyl group is the nucleophile for that reaction that converts us from the chain to the ring. And it gives us a 6-membered ring. I like that. So now for beta, let's just do the same thing that we did with alpha. Start off drawing our 6-membered ring. Okay, so this is beta, right? So if this is beta, I know that my OH is going to be where? On the topmost portion, and then my R group is going to be facing down. Everything else, though, is exactly the same. Okay, and so let's just number out our carbons. So 1 from there, 2, 3, 4, 5, and then 6. All right, so let's circle those so that we know that we're not, I guess, losing track of the distinction, although you should be able to tell pretty clearly who's who. All right, so for the 5-membered, or furan rings, if you could think about them, I'll do those in, I guess I'll stick with the gold nomenclature that I'm having here. So with the 5-membered rings, there's both alpha and beta forms as well. And just how we said the 6' carbon here is the nucleophile, I love that in the 5-membered rings, the 5, that's a 5 by the way, prime hydroxyl group is my nucleophile for these reactions here. And I think that's so nice that it filled out that way. But anyways, for alpha, let's draw out the structure for that. So imagine this 5' hydroxyl group comes in, attacks here, we have the same process that we had before, but this is going to be the end result of our product. So I start drawing these off like I was if it were a furan. So furans all have this common structure in them, or that structure in common. God, I can't talk. So if it's alpha, well, the OH is on the bottom, and then the R group is on the top. And then everything else is just literally fill in the blanks. So the OH in here is going up, this is going up, this is going to be going down, just how this guy was going down. And then it's kind of hard to fit this in here. I'm just going to draw it kind of branching off like that to show that it's the OH part here. Fill in my hydrogens real quick. And that's the structure of alpha glucose. I always think of it like it's cis with regards to the ethanol, or the methanol groups, sorry. They're kind of like both pointing out at they're holding their hands up, waving high at you. Happy alpha fructose. Alright, so now let's number them. So this is 1, 2, 3, 4, 5, and 6. Okay, so 1 from there, 2 from there, 3 from there, so on and so forth. And then notice that it's the 5' hydroxyl group that acted as the nucleophile for this reaction. So that's alpha. Let's circle this in gold if we can to make sure that we're not running out of room for any of this. So alpha furan. Beta is, well, it's exactly what you think it is. So let's start off by drawing our furan. I don't know why I'm hesitant to give myself a lot of room. I've already done everything else. So just like before, we have one going up, the other going down, and the rest being kind of that link for the 6th carbon. 2, there's the OH. That hasn't changed. That hasn't changed, but what has changed with this? Well, it's beta, so the OH is on the top. Form before I finish circling this, let's go ahead and number our carbons. Carbon 1, 2, 3, 4, 5, and 6. Alright, so that's the differences between all the cyclic forms that fructose can take. Take notice of the structures of them. Which do you think would be more stable, unstable? Think about the chair conformations of these, or